All right, what I'd like to do is I'm going to go through the PowerPoint slides that we've done in class and just kind of talk through them again. I know that a lot of people have been having a little bit of difficulty putting all the derivative applications together. The derivatives most of you are okay with, but the applications have gotten a little bit difficult for some. And so I just wanted to take a little bit of time to talk through it with you again so that you have that opportunity to look through it and to reason through it if you need a little bit more time and a little bit more help. All right, so let's go ahead and start. The first thing that we discussed is that there are various quantities that vary with time. And we took some time in class to talk about these and name some. We named distance. Oops. Sorry. There we go. Distance. Right? Your position changes over time. We talked about, like back when we did trig, the tide, the height of the water. You can talk about, oh, somebody brought up love. Was that you, Nash? Said that love changes over time. So lots of different things that change as time passes. We could go on and on, but I don't think that's the important part of this right now. Okay, so we've got the idea that there are various things that change with time. Now, if you'll remember, we talked about in class that you can find changes using the derivative. And so one of the important uses of a derivative is to help you find how things are changing over time. Okay? Now, when we find something changing over time, let me give you a very simple example. Most of you know that velocity is a change in position or a change in distance over a change in time. Okay, now this we'll talk about a little bit later, but this is actually average velocity, right? You take your initial position, you take your final position, you find the difference, and then you divide it by how much time has passed, the change in time from the start of your measurements to the end of your measurement. However, we can also use this as a derivative. We can say that velocity is the change in the position over the change in time. Now it actually looks like a derivative. Remember that when we talk about a derivative, that's all it is it's talking about the change in something over the change in time. However, the derivative allows us to find an instantaneous change. And so it allows us to find the instantaneous velocity at a specific point, which this, of course, is then equal to s prime, right? Prime meaning the first derivative. So that kind of hopefully reminds you a little bit of what this derivative stuff is and what we're looking at. So let's go through a couple of examples and talk through the uses of this. Okay? Part of the hardest details here is the fact that you have to really understand what a derivative is telling you, and when a question is asking you for the derivative and when it's just asking for the original function. So here we've got a psychologist who says that the ability of a person to understand spatial concepts is given by this function. It doesn't really tell us what that ability means. It just says that there's some quantity that measures this ability, all right, where t is the age and a is the ability. So recognize that a is the ability, right? Because that'll be important later on as we go through. Okay? Now, letter A says find the rate of improvement in ability. Okay? So it's not asking for the actual ability when they're 9 years old or the actual ability when they're 16 years old. They're asking how is that ability changing? What is the rate of improvement? Well, if you were to take this and just draw a sketch of it, you should know that a quadratic graph, or sorry, a square root graph, which is a power of 1/2, looks something like this. The 1/3 in front is going to cause a vertical squish, so without a scale, this is more or less the right thing. You can see that the ability, right, because this is ability over time, the ability is increasing, right? Further proof of that is just that the slope here is always positive. Now, the slope always being positive means that the derivative is positive, because the derivative at a specific point is the slope of the tangent at that point. And so when it says find the rate of improvement, it's asking for how is this ability changing over time. Rate is something changing over time. And so what we're going to do to find the rate or to find the change is we're going to be looking for the derivative. And so we're going to take that function, which is a equals 1/3, and I'm going to rewrite it as t to the 1/2 because that's going to simplify it. I'm going to rewrite it as a equals, and then I'm going to take the 1/2 and put it in front, which will make it 1/3 times 1/2, which is 1/6, and then t to the negative 1/2 because I need to subtract 1 from the power. So this is now a prime, the first derivative. Now I can take these values. This now gives me not the ability, but how the ability is changing over time, because this is dA dt, the change in ability over time, which is what it's asking for here. And so we can take this 9 and we can plug it in. I may rewrite this now as 1/6 root t. Remember, an exponent moves it down to the bottom. And so we can go ahead and do 1/6 times the root of 9. So that would be 1/18. And then we can do also 1/6 root 16. So when they're 16 years old, which would then be 1/6 times 4, which is 24. And so we can see that the rate, even though the ability is increasing, right, as time progresses, the ability to understand spatial concepts is increasing, but the rate at which that ability is changing is actually decreasing. 1/24 is less than 1/18. So when you're 16, you have your ability to learn spatial concepts, or the improvement in your ability, is going to decrease. So we can see letter B here, explain why dA dt is greater than 0. Well, you can see in the graph the slope is always positive, right? So the rate is always positive. Now the second question is explain why the second derivative is less than 0. Well, even though the rate is positive, the rate is always becoming less and less steep. Less and less steep means that it is decreasing. And so since the first derivative is decreasing, that means that the second derivative must be negative, right, or less than 0, because negative means that it will cause a decrease in that slope. All right, so let's go on to our next slide, which is another example. This is marginal cost. Now the idea of marginal cost is that marginal cost tells me how much it's an estimate of how much it costs for me to make the next whatever we're making. Okay, this is a cubic function. Okay, so I'm going to just throw up a sketch here. Obviously this doesn't really mean anything at all because I just made it up. It probably doesn't have anything to do with this graph here, other than the fact that maybe I have my y-intercept in the right place. But anyway, we've got this graph, right? And so at some point, this is your cost. This is the total cost, right? C. And then X is the number of genes. Okay. So right here, you have a total cost of whatever this is. If you make one more pair of genes, right, it appears that the total cost actually goes down a little bit. Okay, which is fine. You've got a negative slope, so the change in cost actually means that the cost decreases because you're making one more pair of genes. I don't know why that would happen. I'm not necessarily an economist or a businessman, but you know, that's what this is saying. Now, at some point, right, you're going to be over here, and the next pair of genes is going to cost so much more. And so as you go through from point to point, you're finding out what is the change in cost? How much does the cost go up if I create one more pair of genes, right? So this going up is the change in cost. This going over is the change in the number of genes, which is rise over run, which is slope. Okay, so marginal cost, or the derivative, is dc over dx. dc over dx, of course, then is referring to the change in cost for each change in pairs of genes. So to find the marginal cost, we're just going to do the derivative, which is fairly easy because it's a polynomial. So we'll take the 3 and bring it in front. So we'll go 0.00 0.09x squared plus 0.04x, because I'm taking the 2 and bringing it in front, subtracting 1. And then I go plus 4, because I take the 1, I bring in front, then it's x to the 0, which means the x is gone. And of course, the derivative of a constant is a constant. Remember, if you have pluses and minuses, you can do the derivative of each piece individually, which is what I just did. So this is equal to c prime of x. All right, now I'm not going to actually do the mathematics because there's no point in me pulling out a calculator and showing you how to push buttons because you're all pretty good at that. When it says find c of 220, then all you're going to do is you're going to take 220 and you're going to plug it in for x. Now, when you plug it in for x, that's going to give you the slope of the line at 220. What that's going to do, so let's say that this point right here was 220. What that's going to do, sorry, 220. If my hand will do what my mouth says, then we'll be just fine. Okay, so at 220 you have a certain cost. This, however, is giving you the derivative, which is the slope, which we were just talking about and saying, okay, the slope essentially will tell me what is the increase in cost for the increase in the next pair of genes. Now, if you'll remember back when we did derivatives before, this line actually is going to be tangent, and so it's not going to go through that second point. So this is actually just an estimate. It's an estimate of how much will it cost to make that next pair of genes. So you should be able to plug in the 220 to the derivative function and say, well, the 221st pair of genes costs this much money to make. And so that would be letter B. Now, letter C actually has you calculate that cost. Now, you can see that this is going to take a little bit more work because I'm going to have to take 221 and plug it into the original equation and find out how much it costs me to make 221 genes. And then I'm going to have to take 220 and plug it into the function and find out how much it costs to make 220 genes, and then I'm going to subtract. And that difference will give me the actual cost for that 221st pair of genes, because that's the difference between making 221 pairs and 220 pairs. So these two essentially give you the same thing, though this is a quick estimate because you only have to plug in one number, and then this will give you the actual value finding two numbers. Okay, with only doing one, it's probably better to just do this. However, if we have several different pieces of information that we're looking for and trying to put in, the derivative function can be actually quite helpful. Okay, now letter D asks us to find the second derivative, and so we're going to find the second derivative, which means we're going to take the first derivative and do it again. So we're going to move the 2 in front, so we're going to have 0.0018x, and then I'm going to take the 1 and bring in front, so it'll be plus 0.04, and then that is our second derivative. And so from here, you will now calculate the second derivative. You can put 0 in and you can solve for x. Again, I'm not going to take time to do the numbers and the button pushing. You can do that. Once we have the second derivative being 0, remember this is talking about the derivative. And so if the second derivative is 0, it means that this is at its maximum or minimum rate, because at that point it is not changing. Okay, it is a stationary point of the derivative, and if the derivative is stationary, that means that the derivative is not changing anymore. Okay, so if the derivative is not changing, then the derivative itself is at a maximum or minimum. We've gone into this a little bit more lately, and we understand that when the second derivative is 0, this is our inflection point. And so if you think about that here, that's when you're changing from this concave down up in my graph to the concave up, which should be somewhere around here in my drawing. Now remember, this drawing was completely made up and probably not anywhere near what it's supposed to be. But right there, you can see that's where our inflection point would be. Now that is where you stop decreasing, right? Because for all these values, your slope is getting more and more negative, and then at this point, it starts becoming more and more positive. And so that's where you stop having a negative change in the slope and start having a positive change in the slope. So in other words, this is where you're going to start getting more and more expensive very quickly, whereas before the next pair of genes was getting cheaper and cheaper because of that negative derivative. All right, so hopefully that was helpful in looking at those. Let's go on to the next one. We didn't necessarily do this in class. We didn't have enough time that day, but we did go on and start talking about displacement. I'm going to go ahead and put this in a second video, and so if you want to see this, then be my guest and go watch the second video. I just don't want these to get too long.